So this lecture is about latent variable scale identification methods. Identification methods, remember scale identification is the mean and standard deviation. And up to this, and so these are ways that you can estimate the mean and standard deviation in your model. The trick is you have to fix other model parameters to do so. All right, so we're going to estimate today the standard deviation of the latent variable. What I'm going to show this for standard deviation, but everything holds for mean, and I'll tell you why and how in just a moment. Still conspiracy theories. Today we're going to use a greater, or now we're going to use a greater response model just to show that we can still do this with greater response. Okay, so we got our greater response model. We're good with it. Ordered logit. Love the ordered logit. All right. So remember, there are two, I mentioned earlier, two types of psychometric model identification methods you need. Number one's empirical identification, number of items. Number two is scale identification, right? And I mentioned there are two different methods. We've been using standardized factors, setting the mean to 0, setting the standard deviation to 1. Technically, we could set the mean to some number. We could set the variance to some number or standard deviation to some number. That sets the scale. We've just been using the 0, 1 because it's convention, right? We could have picked a different set. But if you don't want to do that, if you want to estimate those parameters as if they were empirical priors, to estimate a factor variance or to estimate a factor mean, you have to use what we call a marker item method. Marker items are where we have to fix values of certain parameters in our measurement model, right, on an item to be able to estimate the latent variable variance or estimate the latent variable mean. So for the variance of theta, we have to set one of the loadings or slopes to 1 for one observed variable, right? If we do that, we can estimate the latent variable's variance. But I want to denote something, right? Which item? Would you pick one? Who knows? In other software, the default is the first item per dimension. Let's imagine, Vladimir, you don't want the first item. You want the second item. So I set the first item. Vladimir sets the second item. Do you think we get the same estimate of the variance of our latent variable? No, right? We don't. It's relative. So it depends. The estimate of the variance of the latent variable depends on which item you fix the parameter for. Now, similarly, if we want to estimate the latent variable mean, we have to set one or more item intercepts to 1 to be able to estimate it. Right? So for the mean side of the latent variable, we need to fix intercepts. For the standard deviation or variance side of the latent variable, we need to fix factor loadings or slopes. Right? The other thing I want to note for marker item, I mentioned setting one variable to 1, setting one parameter to 1. That's not also there. It's really more general than that. You could come up with a method where you have the parameters sum to 0. That would do the same. Basically, you need to make a constraint on that set of parameters to be able to estimate it. Marker item was the first type of set of constraint. There was, 20 years ago, there were folks who came up with this sort of sum to 0 constraint, which I like actually quite a bit, the sum to 0 constraint, because then sort of, you spread a contribution out across each of the items for the factor variance. It's not just as abrupt as saying item 1 really contributes versus item 2. But I'll show you pretty much it predominates. Marker items fixing one value is 99.9% of everything that shows up in most of the literature or use cases. So, so to estimate the standard deviation of theta, we have to set one discrimination or loading to 1. And to estimate the mean, we'd have to set one threshold parameter to 0. So I'm going to skip that. It's a little bit harder to implement in Stan because of the ordered logit syntax. Remember, in ordered logit, Stan makes it easy to take a set of thresholds and call them ordered. If you wanted to set 1 to 0, you'd have to break free of that and hard code it yourself. So we're going to leave that alone right now. Under both these cases, the model data likelihood is identified, right? This is what I would call strong identification of the posterior distribution. And we're going to start with a single theta, and we'll show it with multiple thetas in just a second. So here is our model block. We have our ordered logistic. This is our similar syntax for grid response model. The note here is theta follows a normal distribution with a mean of 0, but I'm going to estimate its standard deviation. And because I'm going to estimate its standard deviation, I'm going to come up here and put a log normal prior on its standard deviation. I picked log normal just to show a little variation from exponential. Okay? Now lambda, we have to set one lambda to 1. So I'm actually going to take the syntax I created from the multidimensional case and build it into our unidimensional case using transform parameters. So a init lambda contains all of our estimated lambdas, not the one set to 1. But then we're going to use transform parameters to build a lambda vector where the first lambda is 1 and all of our estimated lambdas show up after that. So in that syntax, well, here's our parameters blocks as well. Here's our init lambda. We have one less than the number of items because we're fixing one parameter. So in transform parameters, our first lambda is 1, and the remainder happen to be the rest that are being estimated. So that's transform parameters. So then our data block, mostly the same. The only difference being we need a hyperparameter for the standard deviations mean and standard deviation for theta. And here's our R data set right here. I'll note with the prior distribution for the theta standard deviation, I'm using a log normal prior, which means the mean of it for these values is 7.39, and the standard deviation is 54.1. So that's really large. We've been using a standardized theta at this point. Pretty large, though. So let's look at results. Look at that. We have convergence, 1.01. Hooray. Our standard deviation of theta is estimated to be 1.75. What do you think? Sound good? I don't know. We had it at 1 before. Does it matter? Probably not. The order stays the same. The width of theta, the range, gets wider. And you'll note here, the first lambda is set to 1. And how you know that this is not estimated is this NA and R hat. That means all the values are the same. Within and between are equal. There's no within variance, no between variance. You can see all of our other parameters as well. And here's our standard deviation chain. Does that look converged or what? That looks pretty good. By the end of this class, how many of you will have one of these up on a wall somewhere in your house? It's art. It really is. I'm telling you. If you do, take a picture, send it to me. I want to see it. Here's our posterior standard deviation density. This is our posterior distribution of our theta standard deviation. And here is a comparison. So this green line is a smooth histogram of the EAP estimates of theta under the standardized factor. The red line is the smooth histogram of the EAP estimates under the marker item. Are these distributions similar? Turns out they actually are. If you were to take the green and stretch it out, you'd end up with the red for the most part. Almost, right? So think of it this way. In the green line, you have a peak here around negative 1.75 or so. And in the red, you have a peak, a small peak here. Those are the two peaks. In the green, you get a peak, another peak over here, and in the red, you have a second peak. So what ends up happening is because we've estimated its standard deviation and it's bigger than 1, we've just pulled the scale of theta to be bigger, right? So here are our estimated values. The red line would be identical. You can see the correlation is pretty much 1, but the difference between marker item and standardized factor is that the scale is a little bit different. And similarly with posterior standard deviations. Because the scale of theta is different, the standard deviations are also different for theta. They're on a different range as well. So they're a little bit different. Interesting? And again, there's has downstream ramifications for our other lambdas, right? For all the estimated lambdas in our model, you can see the marker item lambdas are different than the standardized factor, although they're very highly correlated. And that's because, remember, this parameter lambda is on units of y per units of theta. Well, here units of y are logits. Units of theta for the marker item has a standard deviation of 1.76. For standardized factor has a 1. So when you change the units of your predictor, the scale of the coefficient multiplying it changes as well. All right, on that note, we're out of time for today. So I'm going to stop this video and we'll come back on Thursday and talk about marker items for multidimensional models. We'll also have open time at the end of that because there's only a handful of slides left to talk about anything else. If you want me to show you how to phrase a model, like a multi-level model or something like that, I'd be happy to do it on the fly, or at least try to. Of course, that's dangerous. I'm feeling confident this week, though. I think I can handle it. We'll see. But does anybody have any questions for me before I stop everything for today? All right. Once again, project presentations are next week. I'll be sending out a bit of a rubric for what to expect for grading. The same thing for your project as well. So you'll be getting a few emails through Canvas or Icon in the next few days. So be on the lookout for those. I can't emphasize this enough. Please visit me in office hours tomorrow, 10 to noon. Vladimir's office hours before mine, and then Vladimir's office hours on Friday. If I can be of any assistance at all on the project, let me know. That's what it's there for, to sort of help you get started. Of course, email works as well too. And if you have any other questions or comments, please don't hesitate to ask. For that, I'm going to stop. Have a great day. Thank you for being here. And try not to be super excited about all these empirical priors. I know, just keep it in context, okay? Want to stay level-headed throughout the rest of the week, all right? Not too high, not too low, even though Bayes is awesome. All right. Have a great rest of your week, or a great rest of your day. Hope to see you at some point this week. Take care.